Welcome back to the course of chemical crystallography. In last lecture, we were learning about how to do the space group representations in 2 dimension, and we discussed a large number of space groups starting from triclinic to monoclinic and then to orthorhombic and then to tetragonal. And I would like you to practice some of those and some other space groups which are belonging to these four crystal systems. So now we would like you to concentrate on a new aspect of crystals, where we would like to know how to distinguish between different directions in crystals, how to identify them using some indices, and then we will go ahead and learn how to identify the crystallographic planes using the three indices H, K and L. These three indices that I am talking about are called the Miller indices, those are termed as H, K and L. So you might have seen and you may remember that the Bragg's law states n lambda equal to 2d HKL sin theta. So here that d is the distance in angstrom unit, because we represent the lambda in angstrom unit, and the indices HKL indicate the planes. So it is the designation of planes. So when we are talking about a set of parallel planes, suppose these are two set of parallel planes in a crystal lattice, the distance between these two parallel planes are called as d, and we designate these planes as H, K and L. As a result, we identify this distance as d, H, K, L. So to do that, we need to know how to designate these HKLs, what are the possible values of HKLs, and then we should know the significance of those planes with respect to the axis x, y and z. So to know about that, we need to know about the crystallographic points, directions and planes. So in this subject, in the crystallography, while considering a lattice, we always use a right-handed coordinate system. As is indicated here, the right-handed coordinate system of three axes x, y, z, and coinciding with the edges. So now if we have a point inside a lattice which is designated here as P, then what should be the coordinate QRS of that point P? This point QRS has the coordinates which are the fractional coordinates with respect to the unit cell parameters A, B and C. So in case of a body-centered lattice, we have atoms at the 8 corners, as you can see, the atoms at 8 corners and the atom at the center of the lattice. What are the coordinates of those corners with respect to a given origin, which is 0, 0, 0? The ones which are 1 unit along x, 1 unit along y and 1 unit along z are designated as 1, 0, 0, 0, 1, 0 and 0, 0, 1 set of coordinates, set of points, because those are at 1 unit away from the origin. Then the other corners, which are now here 1, 2 and 3, they are first 1 unit away along x, 1 unit above along z, and 0 along y, so this point is 1, 0, 1. Similarly, from here you go 1 unit along y, you go 1 unit along z, and not going anywhere along x means it is 0, 1, 1. So like that, the opposite corner of origin becomes 1, 1, 1. We travel 1 along x, 1 along y, and 1 along z, so it becomes 1, 1, 1. The point at the center of the lattice, which is a body-centered unit cell, then is half, half, half. That means from the origin we traveled half along x, half along y, and then gone halfway along z, and reached the center of the lattice and designated it as half and half, half, half. So for your homework, you find out the coordinates for lattice points for the FCC unit cell. So now let us try to identify the crystallographic directions and the corresponding Miller indices for that. Once again, we use the right-handed coordinate system to find out the coordinates of the 2 points that lie on the direction. Suppose if this is the direction, I want to find out the 2 points, the bottom point and the top point, and determine the corresponding coordinates. Then you subtract the coordinates of the tail point from the coordinates of the head point to obtain the number of lattice parameters traveled in the direction of each axis of the coordinate system. Then by doing this subtraction, if you end up getting fractions, you clear the fractions and reduce the numbers to lowest integers. Enclose those numbers in square brackets, clear fractions if obtained, and if you have a negative sign produced, replace the negative sign with a bar, and then that number, the set of 3 numbers, are called the Miller indices of that particular direction. So here are 3 examples at the bottom. The extreme left one, I want to know what is the direction from this point, which is 0, 0, 1 to 0, 1, 1. So the tip is 0, 0, 0, 1, 1, the base is 0, 0, 1, so I am subtracting the base coordinates from the tip coordinates and I am getting the number 0, 1, 0. So that 0, 1, 0 should be written in square bracket, and the particular direction indicated here in green is the 0, 1, 0 direction. So these are the Miller indices of that particular direction. Let us see the second one. Here the direction is from this corner, which has coordinates 1, 0, 1. From there we are trying to find out what is the direction towards the origin. So the origin is the tip, the base is 1, 0, 1. So what we have on subtraction, minus 1, 0, minus 1. So when we represent it within third bracket or the square bracket, then the Miller indices for that direction is 1 bar, 0, 1 bar. In the same manner, in this case you have from 0, 1, 1, we are trying to find out the direction which is the middle point of this edge. So this is 1 along x, half along y, and 0 along z. So this 1 half 0 is the tip and the base is 0, 1, 1. So on subtraction it becomes 1 minus half minus 1. So now we have a fraction here. So this fraction has to be cleared. So we multiply these 3 numbers by 2 to remove the fraction. So it becomes 2, 1 bar, 2 bar, and that 2, 1 bar, 2 bar is the Miller indices for that particular direction that we have seen now. Now let us do a few more, because I would like you to learn this and do it yourself, and we should do it from the scratch again, because there are some aspects which I would like you to understand here. So I am drawing a cube, and I want to know what is the direction from this corner to the other corner. So this is a body diagonal. So the starting point, origin is 0, 0, 0. The ending point coordinate is 1, 1, 1. So if you subtract the coordinates of base from the tip, you get 1, 1, 1, and hence the direction that we have got has Miller indices 1, 1, 1. Now if we try to see the direction from this corner to the other corner of the unit cell. So what is the coordinate of this corner? It is 1, 0, 1, and the tip is 0, 1, 0. So if we subtract 1, 0, 1 from 0, 1, 0, what we get is minus 1, 0, minus 1. So immediately, 0, 1 minus 1, 0, 1 minus 1, which means the Miller indices for that plane, for that direction will be 1 bar, 1, 1 bar. Now you compare these two directions. They have same indices 1, 1 and 1 with a different sign, minus on two cases, and they are body diagonals. So these body diagonals are equivalent directions, and they can be represented as 1, 1, 1 within this greater than and less than sign. It means that you are referring to all the planes which can be formed by combination of 1, 1, 1 with plus and minus signs on each. So 1 bar 1, 1, 1 bar 1 bar 1, 1, 1 bar 1, and so on. All possible combinations would represent one or the other body diagonal having different directions, and they are called the equivalent directions. The next one that we would like to draw here, a direction with fractional coordinates in it. So we start from a point which is half, 0, 0, and we go to another point here which is 0, half, 1. So we are trying to find out the Miller indices of that particular direction. So we should do this. 0, half, 1 is the tip, and half, 0, 1 is the base. So we should subtract the base from the tip. So we get minus half, half, the base is 0, minus half, 0, 1. So now we have two fractions. So we need to clear the fractions. By multiplying by 2, we convert it to -1, 1, 2. So the corresponding Miller indices for that particular direction is going to be 1 bar, 1, 2. So this is how one should generate the Miller indices of the directions. So for a cubic unit cell, the symmetry of the geometry means that many equivalent directions can be combined into a family, as we have indicated. The spacing of atoms in those equivalent directions is the same. So when we say edge direction, we are talking about the directions 1, 0, 0, 0, 1, 0, 0, 0, 1 and all combinations with negative signs of 1. These are the directions along the edge. The face diagonals will mean they are of the family 1, 1, 0, and the body diagonals are of the family 1, 1, 1 that we already have seen. And directions with same indices without regard to the order or sign are also can be classified as equivalent directions. What are two things to be remembered? Directions are vectors. So a direction and its negative are opposite directions. That means if we write 1, 1, 1 and if we write 1 bar, 1 bar, 1 bar, that means these two are opposite directions. If 1, 1, 1 mean a direction left to right, a direction 1 bar, 1 bar, 1 bar would mean right to left. Directions and its multiples are identical. That means 1, 0, 0 is same as 2, 0, 0. So in case of directions, one should always reduce the HKL indices to their minimum value and write that as the correct Miller indices for those directions. So what is the relation between these two directions, 1, 1 bar 1 and 1 bar 1, 1 bar? The answer is antiparallel or opposite directions, because here the one which was plus is now minus, the one which was minus is now plus, and the one again which was plus is now minus. So in the same manner as we saw 1, 1, 1 and 1 bar, 1 bar, 1 bar are opposite direction, it applies for other combinations also. So I would like you to practice at home that determine the Miller indices for the direction between the following points. There are 5 such examples I would like you to do yourself. Now I would like to move to the crystallographic planes. We would like to designate the planes in the same manner as the directions using 3 indices H, K and L, and we try to determine those Miller indices by using a procedure which I am going to describe now. So what we need to do is we have to identify the plane in the lattice. We need to find out the intercept of x, y, z coordinates in terms of lattice parameters. If the plane is passing through the origin of the unit cell must be moved to a suitable position such that the origin does not coincide with the plane anymore. Then one should take the reciprocal of these intercepts, clear the fractions, but do not reduce to lowest integer, which is different from what we saw in case of directions, and then enclose the resulting numbers in first bracket, and negative numbers as usual should be written with a bar. So let us see the case of a few examples. So I have drawn a cube, and in that, as usual, this is my x direction, this is y, and that one is z. Here I want to designate a plane which is like that. This is one face. So what are the intercepts of this face on x, y and z? You see, this face is parallel to both x and z. So this face is not going to have any intercept on x and z. That means the intercept of this plane with x and z are infinity. And this plane meets the y-axis from the origin at a distance 1. So these are the intercepts. So if I take reciprocal of these intercepts, I end up getting 0, 1, 0. There is no fraction to be cleared, there is nothing to be reduced or anything. So the Miller indices for that plane is 0, 1, 0. Now let us see a different plane. The plane which is here. So the intercepts are 1, 1 and 1. The reciprocal is again 1, 1, 1. So the plane is simply 1, 1, 1. Let me draw a few cubes here so that we can continue drawing the Miller indices for a few set of different planes. We have seen that the plane which is here is designated as 0, 1, 0. What should be the designation of that particular plane? You see that this particular plane is passing through the origin. So we need to shift the origin to a suitable location such that the origin is no longer on the plane. So instead of having x, y, z like that, I would shift this origin here so that this direction is plus x, plus y, this direction is plus x, the backward direction is minus y, and so on. So now with respect to this new origin, this plane is parallel to x, parallel to z, and has y-intercept minus 1. So the intercepts are infinity, minus 1, infinity. So on taking reciprocal, it becomes 0, minus 1, 0. So the Miller indices of that particular plane is 0, minus 1, 0. what do we see? These two planes are parallel planes. They have the indices same, but the sign opposite. Now let us see a situation where we are trying to draw a plane which intercepts at half on both all the three x, y and z. So the intercepts are half, half, half. So the reciprocals are 2, 2, 2, nothing too clear. So that particular plane should be designated as 2, 2, 2 plane. Now if you remember, the plane which was like this, connecting the three diagonals, three corners, that plane we designated as 1, 1, 1. You see now the 1, 1, 1 and 2, 2, 2 are set of parallel planes, but they are different. The plane 2, 2, 2 covers a smaller area inside the unit cell compared to the area covered by 1, 1, 1 plane. So now on the third box here, I would like to draw a plane like this. The intercept here is half. So that means along x, y and z, we have this plane which is parallel to x-axis, that means x-intercept is infinity. Along y, it has intercept half. Along z, it meets z at 1 unit away from the origin, so z is 1. So now take reciprocal, so it becomes 0, 2, 1, which means the Miller indices for that would be nothing but 0, 2, 1. Now let us see a different situation. Suppose we want to identify the Miller indices of this particular plane. This has intercept 1/3 with respect to that origin. This intercept here is half. And here this intercept is 3/4. So now with respect to the origin located here, it is difficult to find out where this plane would go and meet x, y and z. And also this origin is not sitting on this particular plane, but still we can move the origin to a suitable position such that we can easily determine the intercepts. So what we would do is we move this origin from here to the other body diagonal point, which is here, and we write it as a new origin. So with respect to that, this is the plus x, this is the plus y, anything above is plus z, and anything below is minus z. So now with respect to this new origin, what are the intercepts? The intercept along x, along this direction, which is here, is minus half with respect to that origin. On y, earlier it was plus 1/3 from that origin. Now this origin, this becomes minus 2/3, and the z intercept, which was 3/4 with respect to that origin, means it is measured from the bottommost position here to that point there. So this was 3/4. That means now it has become 1/4 with a negative sign because it is downwards. So the new intercepts with the new origin are minus half, minus 2/3, and minus 1/4. So now we would like to clear the fractions. So when we try to clear the fractions, first we need to take the reciprocals. So when we take the reciprocal, it becomes 2, minus 3/2, and 4. So now we need to clear the fractions. So when we try to clear the fractions, we multiply by 2. So it is minus 4, minus 3, minus 8. So the Miller indices for that particular plane becomes 4 bar, 3 bar, 8 bar. Now I would like to give a homework for you to do and come back in the next class, and we will see how this can be solved. So in this particular cube that I have drawn here, x, y, and z as usual, I am drawing a plane which is having an intercept on z axis here as 4/5, and it has again an intercept on z axis at 1/6, and this is the plane. What would be the Miller indices for that plane is an assignment for you.